Okay? Okay. I love doing this recursively, and I actually think it's a simpler code to do it recursively. So for these, notice in-order keys visits all of the nodes in order and accumulates the keys. Our keys are all integers, and remember, when we do this in-order traversal, or any of these traversals, we end up kind of smashing the tree into a single dimension, to one list. So that's why it fits as a list. Yeah? So to do this, I'm going to follow the same pattern that I've followed with all the other recursive methods, which is non-recursive starting point and then a recursive helper function. So I'm going to create a private void, because in this case, I'm going to not return something, I'm going to accumulate it. I have a private void in order keys recursive. Okay, so you see my my pattern is to take the same name and make it, add the word recursive to the end. All right, with recursive method, we want to think about what is the input to a recursive method. And with recursion, I guess you could do it either way, but you absolutely have to say, what's the starting point? What node are we going to be starting on at this iteration of the recursion? So I need a binary search tree node of generic T called node. And the other thing that I need is my list of integers of the keys, because I need to know what are the keys that I've accumulated so far, and I'm going to append another key to it as I visit it. Yeah? So I need this as input, but it's also kind of output as well, because I'm accumulating the keys that I visit there. Okay. And just to show you the starting point, I think I'm going to write this property as a, I'm going to like hand code this. I'm going to write a getter. So here the getter is, I'm going to create keys is equal to a new list of int. So this is an empty list, but it's a list that has memory now. Yeah. And then I'm going to start my recursion by calling in order keys recursive, passing in, like, where do I want to start? The root, right? I want to start at my root, the root of this tree, and this variable keys. And once I've done all of the recursion and accumulated all the keys, then I can return this list of keys. Does that make sense? And this will be the in order keys here. So, like most recursive things, I am in my non-recursive starting point calling the method on the root. And in this case, I'm also passing in an empty accumulator. So the very first time I call this, I'll be at the root of the tree. Do y'all remember from last time, what's the structure of every recursive method as I laid it out? You remember that there's got to be at least two parts, two cases, if you will. We need the base case and what I'd call the recursive case. What is the base case? What is a base case? In this case, there is just one. How do we know when we're definitely done? Yes. If the node that's passed in is null, then we can just return. Because if it's null, there is nothing that we can add to this list of keys. There is no key. This is going to be the case. Imagine like the simplest possible case is, what if we pass in an empty tree? If we pass in an empty tree, then root is going to be null. But that's the first thing we check is the node that we're on null? If it is, we're done. And in that case, did we change keys? In this code, did we change keys? No. Keys is whatever it was to begin with. So in an empty tree, keys will be an empty list. So that makes sense. So even if we can't see the whole picture, we see that one simple starting case. But it also should make sense. If you ever get to the bottom of the tree and you're visiting a left child that doesn't exist, that's null, then you can't do anything and you're done there. Okay, so the recursive case, I would like to remind you, what are our 3 steps for in order? It's on the board. Left, root, right. Yeah, left, root, right. Yeah. All right, so what does it mean to visit the left node? It means we call in order recursive on what? This is the method we're in. It takes in a node and it takes in a list of keys. I'll do the second part. We pass in the keys. What do we put here? Yep, that's it. So we go to the left. So this is taking care of the left. What does it mean? Well, actually, while we're thinking about it, you want to do right? Let's do right. In order recursive, we definitely want to go node.right and pass in our keys. So that's steps 1 and 3. What is step 2? In this case, what does it mean to visit the root? And I'm saying what I want us to do, the work that we're doing, is just appending the key onto the list. So to do that, all I have to say is keys.add, and I want to add the current node's key. And it must have a key because it wasn't null. We're getting these little warnings here that saying, hey, node.left could be null or node.right could be null. And that's true. What it doesn't know with the compiler or the linter, we're going to take care of that. If we call this again and this is null, if one of these is input is null, we'll take care of it here and won't proceed. We're going to handle the null case, but apparently it can't tell that. Up here. Good call. I guess that's fair to say. We definitely are going to allow this to be null. Thanks, Robert. So I think this is beautiful and elegant. All that work that we went through on the screen and standing up on the board. Like I almost have as many lines of comments as I have lines of code to do it. It's that simple. And I believe this is right. Let's check it and see if our I was failing 55. Let me see if I pass any more now. There may just be one test for in order. I bet I didn't write more than one in order test, so sweet. Also from this, I hope you can tell, if you have code that works for in order, how close are you to pre-order and post-order? Super close. Like it's a matter of like, doop. That's it. I mean, just you got the structure here, so that should be it. All right, we hit that. For some reason, a method that I really like is height. How do you compute the height of a tree? It's based on levels, all right? How do we count levels? Children. Um, I would like to do this recursively. If we were to look at this tree, which is not a binary search tree, it's just a binary tree, and we would like to know the height of this tree, you can look at it and see, well, what is the height of this tree? I would call it 3. And in some sense, then you could say it's the maximum number of lines deep that any path is. We don't have it here, but if I have a child, which I do, I have 6. Logan is my child. In this case, now the tree has a height of 4. 1, 2, 3, 4. Sure, it's the case that this is only 2 deep. 2, 3, that's only 3, but it's the maximum, right? And if Logan had a child, then this is imbalanced, but it would be another level deep, the height of our tree, yeah? If we're going to do this recursively, then, which I think trees lend themselves to, we have to define 2 things. What are the 2 things we have to define if we're making a recursive implementation? You know this, right? It's insulting that I'm asking you. A base case and a recursive case. What's our base case here? We can't think about the whole thing. I mean, it's true. All right, there is this special case. If the tree is empty, then we can decide, does it have a height of 0? Or I guess it does. And if you add one thing, it still has a height of 0? I'm fine with that definition. If I give you a particular node, is there a time when you know what the height is? Or is there a time you know I don't want to say. Maybe I should just give it away. I don't know how to get you there. I'm sorry. If I were to give you Keenan a leaf node and say, what is the height, or how is Keenan contributing to the height? How would you answer that? If I'm at a leaf node, its height is sort of like, to me, it's 0 plus whatever the current height is. Or you could invert that and say, let me just invert it and say what I want to say. Dylan, the height here is 1 plus the height here. And the height here is 1 plus the height here. And the height here is 1 plus the height here. And if I'm a leaf node, then I'm kind of have a height of 0. Does that make sense? Almost. I'm almost there, but I've ignored an important thing. Does that make sense? So my height is 1 more than the height of my child. I'm actually 1 more than the height of my bigger child. The bigger height of my 2 children. So if I were to say, hey, this is, because this has a child, this is +1 to whatever Adrian's height is. Adrian's height is +1 to whatever Robert's height is. Robert's height, because he doesn't have any children, is 0. Now that I have a 0, then I now have a +0 +1 +1, which is 2. So the height on this path is 2. This path would have a height of 2. This would have a height of 3, 3, 3. So the full tree's height is whatever is the bigger height of your 2 children. And that recurses down. Does that make sense? So that's a recursive definition of height that I think is really suitable to implementing. So I think you do. Yep, unless you store it. I don't follow you. You're saying, no. If I give you 7 keys, if I know that there are 7 keys in the tree, it could be 3 tall, or it could be 7 tall, depending on how. Yeah. Okay, so here's our setup again. I'm going to have a private int height recursive where I have this helper function. And the height recursive needs to take in a node, which is a binary search tree node in T. And it's going to return the height. Sorry, I need to give this a name, like node. And then up here in height, I need to have a getter, and my getter should say, actually like that. If it's empty, return 0. Otherwise, return. Did I just delete my recursive method? Well, that's unfortunate. Hang on, I'll fix it in a second. I'm going to return, not root to height recursive, starting at the root. And now I'm going to copy this and undo so that I get back. How did I do that? There we go. This. It's true, Evan. If you have a count of 1, then you have a height of 0. And if you have a count of 0, then you have a height of 0. I think those two you do know in all BSDs. But those are kind of not especially helpful. Right. Those 2 counts do directly inform what the height is. But beyond 0 and 1, I don't think you know. I guess no, you'd know 2 as well, and 3. No, you would know 3. 2 is a height of 1, but 3 could be a height of 1 or a height of 2. Unless you're balanced, which we're not balanced. We're not guaranteed that. Okay. This is mad at me because not all code paths return a value. Sure. Okay. So I am handling this one case here. If the tree is empty, I'm just going to go ahead and say the height is 0. It feels like something I should do. Otherwise, I come down here. All right, let's think about our base case. right? We want to have the base case first, because if we don't have the base case, then we have infinite loops. And it sure does seem like the node being null might be one. So I don't have my cheat sheet at the moment, so I'm going off the top of my head. I think it should be 0, but it might need to be -1. Because it's kind of like when you go to the last level here, when you get to these null guys down here, you've already added 1 to get there, but you've got to subtract 1 because they're null. They don't exist. This makes it, I think it's simpler that we're going to say, take 1 off once you find the null node. All right. This is in the book as well. I'm pretty sure the book walks through this. I think we here just need to say the height here is is 1 plus the bigger height of your 2 children. Does that make sense? So if you were really imbalanced and your right child has a height of 3 and your left child has a height of 0, then you're saying then your height as the parent of the right child is now 3 plus 1. So you can use math.max to get the bigger of 2 things. So I would like to get the height recursive of the node, the left node, and the height recursive of the node dot right. So I'm computing the height of the left subtree and the height of the right subtree recursively. I'm adding 1. Every time I go down, I'm adding 1. Except for the last time, I'm kind of undoing the addition of 1 because you couldn't actually go to another level when it was going to a null node. Otherwise, you'd be off by 1, which might be okay, but it's not okay. I feel like this is the essence of it. Let's see if it works. Does this make sense to you? What questions do you have on this? We start at the root. In this case, at least the root is not null because we already caught that here. So if the root is not null, then at least on our first time, yeah. So we don't know what the height is yet. We're going to say 1 plus the height of the left and the height of the right. Let's imagine we just have a root and that's it. So we go to the left. When we go to the left, if I just have a root, this is a whole new tree right here. The dotted lines mean this is null. Then I say it's 1 plus the height of this. Okay, so I have kind of a plus 1 hanging out here. I get to null. What's this? The height of this null node. We just said return what? Return -1. Okay. So let me also compute the height of my right subtree. I go down. This is null. So that's a -1. Okay. Which one of these two, -1 and 1, is bigger? They're the same, so it doesn't matter. It's -1. So then I would say here, it's 1 plus -1, which is 0, is the height of this that I've written here on the board. TV. Does that make sense? Okay. So maybe you want to extend it 1 and think, okay, well, let's imagine it actually does have a right child, which means it has these. And there's some data in here. So we add 1 here. I'm going to add 1 here. I'm going to add 1 here, add 1 here. When I get here, I get a -1 and a -1, which I see that kind of like cancels out. And at this point, then these cancel out. The height of the left subtree is 0, and the height of the right subtree is 1. Which one's bigger? The 1. So the height of this whole thing is 1. Does that make sense? It's elegant, right? So, I mean, did you all run this? Does it work? It passes the test? Sweet. Can you imagine how you'd have to do this iteratively? If you wrote loops to go through the whole tree, how would you do that? To me, it's much less apparent, and it would take a lot more bookkeeping to kind of keep up with what's the deepest path you found so far. And then I still want to use a stack for that to kind of backtrack. I don't know if you could do it without a stack. I'm sure we could ask ChatGPT, and it probably would know how to do an iterative implementation of height. Okay. All right, we got 7 minutes at the most. Remove is hard, but we walk through all those cases, and you should absolutely do next or previous. Isn't that what I called them? Or did I call it predecessor? Okay, range search. I mean, summary. Return all nodes with keys between min and max inclusive. Do you guys know this triple ///? If you do the triple slash, it's a documentation comment. Because I put it right before a method, VS Code knows that I want to have that. VS Code knows to write in this special comments where there's a summary kind of element, and each parameter has this. So this is the minimum key. This would be the maximum key. And when you do this, now if I were to call this later in my code, I get like IntelliSense right here, range search. You see this? That's what I just wrote in that comment. Have we done this before? So maybe if I were more on the ball, I would have written all these for you already. But actually, I wanted you to be able to generate this from scratch, as it were. So the inclusive means greater than or equal to min and less than or equal to max. Does that make sense, Annika? So you're going to find a list of binary search tree nodes of type T whose keys are greater than or equal to the min and less than or equal to the max. Is there anything else that's unclear here? I mean, did we write get node? If you have get node, your life gets a lot easier. If you have get node, then contains is trivial. We're saying does it contain the key? If I say var node is equal to get node of the key, and then if I say, right, basically I'm returning contains means return that node does not equal null. Isn't that it? Which I almost don't even need this line. Sorry, don't need that. This is a Boolean condition. Does get node, is it non-null? If you get back a non-null memory address, that means that there is a node that has this key. If get node works. Does that make sense? So I think that's a simple, clean way. I don't know if this is readable. Do you think this is readable? So is there, if you don't, get node should return null if it can't find that key. So if it returns null, then I want this whole thing to return false. I don't know. You should probably test this. You absolutely should test it. What were we at before? Like 48? Was that 48 failing? 47. 47 is not 48. Maybe there's just one contains. Next is successor, in order successor. Previous is in order predecessor. So, and remember, we know the geometric, we talked about the geometric meaning of that. Do y'all remember that? For next, what's the next node? Your blank child's blank most child. In order successor. It is your right child's leftmost descendant. So you go right and then go as far left as you can go. And that has to be, I mean, go until you hit null. Same with, or in an inverted way, predecessor is your left child's rightmost descendant. Yeah? Okay, when is this due? Friday? That feels doable to me because this is all you're doing for me in this class, right? Does that feel doable to you? Okay, so I want y'all to like make a solid effort to get a lot of this done by Thursday and bring in like real intelligent questions. You know, the kind of questions that I don't like. The questions are, I hadn't really started on this because I didn't know what to do. You feel me? Like that doesn't feel like solid effort. If that's where you are, then let's talk before then. But do this. It's possible I've made some mistakes in unit test or whatever. So I definitely would love to know that earlier. And I do want to start talking about another kind of tree on Thursday, if possible. Basically, I mean, this is binary search trees. And we know their Achilles heel. What's the Achilles heel of the binary search tree? Yes, they get imbalanced. And if they get imbalanced, then we lose all the benefit. Because if they're just a long linked list, then that's a bunch of work to look up. So we'll talk about how to balance these trees I think next time. Median key means the middle key. So if you have an odd number of things, it's the one in the middle. If you have an even number of things, I want you to find the two middle keys and average them together. Great question. All right, see you guys.